Okay, we are recording. So, last time we were talking about functions of several variables, and we just kind of barely got started on this. And let me just remind you of really the big point to start off with is what a function is. Very commonly misunderstood. A lot of people think a function's a formula. No, it's not. It's absolutely not. It is a trio. It is a list of three things. All three of these are part of what defines a function. And so the example that we ended with, as I recall, was this right here, that these three functions right here are all different functions, even though they all have the same formula, right? Let me do it like this. They all use the same formula, right? But they have either different domains or different targets or both, right? But the point is they have differences among their domains and targets. So these are three distinct functions, even though they all use the same formula. Yeah.
Is the target the same thing as the range?
I'm going to talk about that in a couple minutes. Yeah, great question. Great question. Okay, before I get to that, let me define something called the image. The image of a function is the set of actual outputs. So what actually comes out of the function. Now, let me first distinguish this from target. The target is the set of allowable output values, right? The image is the set of actual output values. So here's the contrasting example. Here is a function, perfectly good function. The target, you see, is R. I've set this function up, as I have it defined here, where any real number is allowed to go in, and as far as I'm concerned, any real number is allowed to come out, right? So the target is all real numbers. But now let's think what actually comes out of this function, right? If you take real numbers from this domain, if you square them, you will never get a negative number, right? So the image and the target are not the same, right? Those are different things. The relationship that you can say, the image is always a subset of the target. Okay, so now to your question, what's the range? Sadly, that means different things to different people, and it's very frustrating. Because if you're going to if you're doing math, you need to be able to communicate with precision. That's kind of what math is all about, right? And if you don't know what your listener will interpret from what you say, then that's just not good communication. So I try to never use the word range, other than to say I don't ever use the word range. And if I mean target, I'll say target because I believe that's universally agreed upon as to what that word target means. And likewise, I believe it's basically universally agreed upon what the word image means. Range kind of has been ruined by confusion. Okay. All right, moving along. Now, what I've defined here to be image is this is the image of a function. I'm going to now talk about a slightly different usage of the word image. And that is if you are looking at a function, and if instead of wanting to know the image of the entire function, if you just plug in one single input value, and you want to know what comes out of the function, for just that one single input value, that single output is called the image of that input. Right, so we've got to distinguish between the image of a function, which is all the possible outputs, versus the image of a single input value, which is the single output value. All right. So analogously, if given an input, if the output is called the image, I think it's a reasonable choice of words. Given an output, the input is called a pre-image. It's just terminology, but the idea is if you take an in and get an out, then you're sort of going in the direction that the function's going. If you take an output and ask what was the input, then that you're kind of in some sense going backwards. Okay. All right, so image and pre-image, very useful terms. There's some related ideas that we need to talk about, and that these are these terms right here. You'll see from the way this is written that it all boils down to looking at points in the target, looking at the pre-images of points in the target, and asking, can we say whether the number of pre-images is always at least one, or perhaps always less than one, or perhaps always exactly one. All right, so let's see some examples. Looking at this function right here. This function is what we call onto. This function is onto because every point in the target has at least one pre-image. Let's kind of walk through this point here. This kind of weird sort of representative function that I have sort of sketched here. This output value, there is exactly one input value that lands on it, right? Which is at least one. Let's look at the next point. The next point is a little bit different, right? This has actually two corresponding inputs which land on it. Either of these, when you plug it into this function, lands on that given output value. So we would say that this light blue point here on the right, that point has two pre-images. Which again, cool. That is still at least one. Right? And you can go down the list. The point is, once you know what you're looking for, it's easy to confirm that all of these points have at least one pre-image, and therefore this function is what we call onto, sometimes called surjective. Okay. Similar idea. Sometimes you look at a function and you can, at a glance, easily determine that every point has at most one pre-image. Not this function. This function does not follow that rule. After all, this point right here, as we just discussed, this point here has two pre-images. Two is not at most one. But now let's take a look at this function right here. Now I keep circling the wrong one. Let's look at this function right here. This one satisfies the rule. The first point has exactly one pre-image, exactly one, 0. All of those are at most one. So this function is what we call one-to-one, which is an unfortunate terminology, better injective. Yeah?
So would that be an example of the y equals x squared?
Yeah, that's right. Well, kind of. Actually, the y equals x squared function is really, honestly, more like this, because it's neither one-to-one nor onto. Well, actually, we're going to talk about that exact function in just a second. Yeah. Right. Okay. All right. So why do we need to talk about all this injective, surjective business? And that is because sometimes a function is both injective and surjective. In other words, the number of pre-images are always at least one and always at most one. In other words, it's always exactly one, which means it's both injective and surjective, and thus the term bijective. Okay, and why we care about this is because a function that is bijective, you take a quick look at this symbolically, and I hope I can make a case that this is exactly what we need to be able to say a function's invertible. If I want to be able to turn this function around, in other words, well, for every point in the target, the target's going to be the domain of my inverse function, right? If I'm turning everything around backwards, I need to know for every point in the target that I can have exactly one, no personal selections necessary, exactly one pre-image that I can call the value of the inverse function, right? It's got to be exactly one. I cannot invert this function right here. I have too many choices of what should be Which would be the value of the inverse function at this point? I've got a couple options. I don't know which one. Who can say, right? And I have too few options for this point. The inverse function, if I were to try to call it a function, it wouldn't even be defined for that point. There's nowhere for it to go back to. Right? So that's why we need both injective and surjective, and that's why I call this invertible. Okay, so for example, let's look at these two examples here. This function, I believe this is exactly what you were asking about, right? So f of x equals x squared. Now, reminder, if you're going to talk about a function, strictly speaking, you got to indicate all three things. So this is not just the formula f of x equals x squared, but I'm indicating here further that I'm going to consider all real numbers to be allowable inputs, and I'm going to require only that the outputs also be real numbers. And unless you have a particular need to specify more carefully, it is actually pretty easy to just kind of whip down something like this, R to R, one number in, one number out. Let's not get particular. If we don't need to, why would I restrict my domain? Why would I try to give the tightest possible target? Who cares in most cases? But this function, as I have it written down here, is not invertible. Right? 25 has too many preimages. Negative 17 has too few preimages. Right? There's no way I can turn this function around. What I can do is resolve both of these issues by being a little bit more careful with how I define the squaring function. So this is what you might call the invertible square function. Right? So notice only non-negative numbers are allowed in, and only non-negative numbers are allowed out. And with that understanding, totally invertible. 25 no longer has too many preimages. Only 5 is the preimage. Negative 17 is now not my problem, because negative 17 is not in the target, and therefore I don't have to worry about how to work backwards from it. So that function is perfectly invertible, and we have a name for the inverse function. The inverse function is the square root function. So again, a lot of people misunderstand on this. A lot of people think that the square root function is just the inverse of the squared function. No, it isn't. Right? Easy counterexamples. Right? You have to restrict your domain to make it invertible. Okay. Analogously for the sine function, now if you ignore domains and targets and just write down, hey, sine, well, sine is defined for all possible values of theta. Right? You can see if you try to invert this, you're going to have a problem. You don't have this bijective correspondence between input values and output values unless you restrict the domain just so. And now I know y'all are typically most familiar with the sine function thinking in terms of graphs. So think of this as these are the allowed values of theta, and then these are the allowed values of y, namely the sine of theta. And notice this part of your familiar graph of sine gives a perfect one-to-one correspondence. For every green, there's exactly one blue, and vice versa, right? So exactly what you need. And so this function here, restricted domain and restricted target, is invertible. And again, you have to get upset about this little seemingly micro trivialities in order to even be able to talk about arcsine. Right? So arcsine is the inverse of this function. Okay. And by the way, just a quick reminder, even though I know y'all are highly accustomed to seeing graphs of sine, I'll point out that if you need the graph, then okay, there's nothing wrong with that. But honestly, if you don't specifically need graphs, I find it myself very often much more convenient to think about the angle on the unit circle and the y-coordinate on the y-axis. And then very simply, the sine function and the arcsine function both are just understood as just will slide horizontally. If you want to turn an angle into a y, then go to the left. If you want to turn a y into an angle, go to the right. Arguably a simpler picture. So, something to think about. Okay. This last little bit here, I'm going to mostly wave my hands at and let y'all read on your own. All this business here is just terminology, most of which is that we need to have language to distinguish different cases of how many input variables we have. And sometimes there's only one input variable, sometimes there's several input variables, or said differently, sometimes the input is a vector, not a single real number. So watch out for these terms, real valued and vector valued. Likewise, how many outputs we have. We might have one, we might have several. I got that backwards. Golly. Let me try that again. The number of input variables. There might be one variable, there might be several input variables, and thus the term single variable, multivariable. Sorry, I've circled the wrong things. And there might be one or several output values, thus the term real valued and vector valued. Because what comes out might be a real number, what comes out might be a vector. Does that make sense? Sorry about the oops. Okay. All right, read the rest of the details. It's worth a glance. And then I just like to point out very quickly that even though the term vector valued multivariable function sounds sophisticated, this is actually a really common thing to need to talk about. It's not a sophisticated idea, really. So, for example, casual conversations about the weather, right? Super, what's the word? Polite elevator conversation, right? Water cooler conversation, is actually a discussion of a vector-valued multivariable function because there are several input variables. Longitude, latitude, altitude, how high. The weather's very different at 10,000 feet than it is here. Okay. Vector valued, because when you talk about the weather, there's a lot of things to talk about. Temperature, barometric pressure, blah, blah, blah. So don't think of vector valued multivariable functions as, niche, rare things that don't come up in the real world. They're all over the place. Okay. All right, on to how to visualize functions. I'm going to start by talking about graphs, partly because this is the type of picture that I think y'all are the most familiar with. Y'all have been drawing graphs for many years at this point. Rather than go into the definition first, I'm going to start by looking at the standard example that you've seen a million times and worked with a million times. Let's talk about this right here, and then we'll sort of reproduce the definition as motivated by this. The graph, this curve here like this, consists of a bunch of points, like so, for which the first coordinate, you'll notice, is an input value to the function. This first coordinate is what goes in, and the second coordinate is what comes out as a result. All right, so let me say it a little bit differently. The way you form a graph is to take all of the input values, find their corresponding output values, assemble those into ordered pairs where you put the input first and the output second, making therefore an ordered pair of coordinates. And the graph is the collection of all such points. Okay, so this is the example that we're going to work off of to motivate this definition up here, general definition of a graph of a function. Now notice, though, that here we're allowing several input variables, not just one. Several output variables, not just one, and not necessarily the same as the number of input variables, right? So a generic vector-valued multivariable function, and notice it's the same basic idea. Whatever goes in, those coordinates come first, and of course there might be several coordinates because that's allowed to be a vector. And whatever comes out is what comes next, and again, it might be several. And the collection of all of those is what we call the graph of that function. Okay, does everybody see how this definition is just a sort of a generalization of this idea that we're already extremely comfortable with? Okay. All right, now let me explain a different way to think about this, and this is just for intuition purposes and in certain scenarios. It's just very convenient. Another way to think about a graph is that if you have a function, you can write the equation of the graph. Let me see if I can. Oh, come on. There we go. There we go. You can write the equation of the graph by looking at what comes out of the function and setting that equal to a new variable. Right, we start off with this function. This is a function of x. X is the input. F of x is the output. There's no y. Initially, when you're just looking at a function, you need to give a name to the input variable so you can write a formula for the output values, but it's just called f of x. Choosing to label the outputs as another variable is what gives you the equation that makes this a graph. All right, so take your pick on those points of view. They each have their benefits. Again, the graph is represented by this equation. All right, now let's see a generalization of this to a higher dimensional context. Let's think now about a function of two input variables. Okay, so one way to think about it. We have two inputs. Actually, I should do this in green. We have two inputs. Let's call those inputs x and y. The input variables come first. Right? Whatever comes out comes second. So again, notice we put all of our input variables first, all of our output variables last. And these points, let's do it like this. These points formed as such are points on the graph. Everybody good so far? Yeah.
How do we know the output's going to be with this?
Oh, how you draw the picture is kind of up to you. Now, there's a standard convention that pretty much everybody sticks to, and everybody should stick to just to minimize confusion, which is that if you are drawing a three-dimensional axis system, you should always have x coming out of the page, y always going to the right, z always going up. That's just kind of for convenience. It's not really technically required. Yeah. Okay. Now, here's a different way to think about this. Different way to think about this is you can kind of sort of view the domain in this picture. The domain, after all, represents all values of x and y. You might say the domain is the xy plane, which you can kind of see here. A little bit of a sloppy take, actually, because the domain is literally a two-dimensional world, R2. What I have drawn here in green is a plane sitting inside of a three-dimensional world. So it's not quite, this is a bit of an abuse, right? But it's awful convenient, handy for sort of, having a sense of picture. And then the target, all of these output values as well, it's all of the z values. Again, for sort of convenience, sloppy though it is, you can think of this as being the target, the z-axis in this case. Right? So with this point of view in mind, notice if I think of the formation of the graph as starting with all of the inputs, and then for every input, the function tells me how far to push up to get to the corresponding point on the graph. Okay, well then what that means is we're going to be taking the two-dimensional xy plane and pushing it up. Now, by different amounts in different places, right? So we're going to be sort of asymmetrically taking the flat plane and pushing it up. The punchline being that because the domain is two-dimensional, the graph also two-dimensional, such as I have drawn here. And so notice that what I've drawn as the graph is a surface. Surfaces are two-dimensional. Make sure to don't conflate the surface itself, which is two-dimensional, with the world that the surface lives in, which is three-dimensional. Right? Every surface or curve or what have you has an intrinsic dimension, and then there is the dimension of the world where it lives, and those are usually different. Okay. All righty. Everybody all right? Questions? Okay, here's another example. Let me make the observation. That's a single variable example that we looked at in our very first example. This is our, what you might call, very first multivariable example from R2 to R1. This is the simplest possible multivariable example. And yet, if we bump it up one dimension, if we go for the second simplest possible multivariable function, it crashes and burns. Right? It's just a complete losing here because three input variables, x, y, and z, and then let's see here, one output variable, which is w, which means the graph is going to consist of a bunch of points that live inside of R4, and you can't do that, right? That's just, what are you going to do? You can't draw R4. You can't visualize R4. So you can't in any useful way draw a graph. And again, I remind you, this is the second simplest possible scenario of a multivariable function. All right, so this is my first complaint about multivariable graphs. It's pretty rare that we can use them at all. Right? We love single variable graphs. Practically every picture you ever drew of a function in single variable calculus, they're practically all graphs because it works. You can draw the picture. There's a tremendous amount of convenience in the relationships between what I'm going to call the algebra of the function and the geometry of the graph, right? So the algebra of the function is stuff like, what's the derivative? Is it positive? Is it negative? What's the second derivative? Is it positive? Is it negative? Then there's corresponding geometric interpretations. Is the slope upward or downward? Is the concavity upward or downward? Right? So tremendous amount of convenient. What I'll call the calculus of single variable functions is how do we relate the graph of the picture to the algebra of the function itself, and calculus of graphs in one dimension is something y'all are all experts with. Okay. And again, that's by far the best case for graphs. You can kind of just barely do it for functions of two variables. Let me point out, this is a scam of a picture, right? I tried to make it look three-dimensional, but it's not. This is a flat screen, right? When you draw with a pencil, it's flat. It's two-dimensional. This looks like it's come out. I'm trying to make this look like it's coming out of the page. It's not. Right? So this is already a little hacky. Okay. All right, so graphs have a big disadvantage. You can hardly ever use them in a multivariable context. The way we're going to fix that problem is by finding other constructions, different constructions, to allow us to draw pictures that relate to functions. But very, very importantly, they will relate to functions in different ways. They are fundamentally different pictures. So when we're looking at a function then, there's a bunch of different pictures that we might need to use to talk about it. They're not all going to be graphs, right? So while in a Calc 1 class, you can get away with conflating the graph of a function with the function itself, in a multivariable context, you just can't do that. You will absolutely get confused. You'll get some wrong answers. You'll mix and match ideas that don't go together. It's just a catastrophe, absolute catastrophe. So now again, Calc 1, you can get away with this. And I am not aware of any single variable calculus instructors other than maybe me, if I were to ever teach it, right, who would get uptight about the distinction between a graph of a function and the function itself. Because who cares? But at this point, in this multivariable calculus class, you have to get real careful about this stuff. Please don't say function if you mean the graph of the function. Does that make sense to everybody? It's going to get you into big trouble. Okay, so let's talk about some of these other pictures. I like this one. I think this is an underrated, underappreciated kind of a picture that you can draw. It's what I call the literal picture. The idea of a literal picture is that I'm going to take a function. Here's a function that takes me from R3 to R1. I'm going to literally draw these things in this action. So notice R3. I've drawn a picture of it. That's my domain. I'm going to take the target R1 and I'm drawing a picture of it. And this action of a function taking points out of the domain and into the target, I represent with this arrow suggesting that points are moving there to the right. Is that cool? So this algebraic story represented by this geometric picture, and again you can see this is just a picture of literally what this is. Everybody on board? Okay, so pros and cons. Now you can see some obvious cons. I can draw like one input point and its corresponding output point, and I guess I could do a couple of them, and if I get colors involved I might even be able to sort of keep track of which input goes to which output, but where's the shape? Right, there's no shape to see here. Like in these cases, we know what the shape means. The shape tells us important stuff about the function. We are soon going to see that the shape here, the shape of this graph surface, will tell us certain important things about this function. And the geometry that comes, or the algebraic knowledge that comes from understanding these shapes, super helpful in a lot of ways. And here we get none of that. So why am I so excited about this seemingly obviously disappointment of a picture? And here's why. The comparison that I just made was a grossly unfair comparison. I was comparing, here I'm drawing a picture of a function of 3 variables, and I was comparing it to these much easier functions that have only 1 or 2 input variables. So the fair comparison is between this disappointing picture of a function of 3 variables and this absolute absence of a picture, right? When you try to draw the graph of a function of 3 variables. So it's not good versus bad that is the relevant comparison. It's absolutely nothing versus disappointing. And when those are your options, disappointing is a win. Does that make sense? Yeah. Oh, I'm sorry. Any questions? All right. Now, I want to point out further. It's not even really that disappointing. maybe we had our hopes set too high. But here's a really nice thing that you can do with a picture like this. Again, supposing that you're at a certain point in the domain and there is a corresponding output value. Here's an example to be thinking in terms of. Let's suppose this is a location, let's say in this room, and the output value maybe represents temperature in this room, which, by the way, is, of course, too high. I can't get the temperature right in here, but I will. Okay, so not particularly helpful. I don't see a shape. Where's the picture? It's not that good. But here's a reasonable thing that you might want to do. In fact, let me say that differently. Something very important we are going to be doing in this class is entertaining the question of, if I were to be at this point and to start moving, right? If I'm standing here and I'm hot, if I start walking this way, I feel like it's getting a little cooler. At what rate is the temperature changing as my location changes? So let's draw a picture of that here. And a pretty reasonable way to draw this picture would be to say, well, I'm going to have some velocity in the domain, and I want to know what the corresponding velocity is in the target, right? So as I walk a certain direction, my temperature is going to be decreasing. My position is changing with time. That means the temperature is changing with time. So I want to know, what's the relationship between my input velocity and the rate of change of temperature as I walk? That's a very natural question. And disappointed though we might be about seeing the function itself, what we do, I think, we have a pretty satisfying picture here of at least what the question is asking. And there's a lot of value in that. So we're going to be doing a lot of stuff on this picture. And very important to notice, it's not a graph. Okay, yeah?
How does W come into play if you have X, Y, and Z?
Yeah, it doesn't really in this case. I just gave it a name just because I could. I guess, depending on what notation you like, you could phrase the question then as compute dw dt. Right? So as I move, this W is going to be decreasing as I have it drawn here anyway. So what is the rate of change of W? So dw dt. That'd be a reasonable use. Yeah. Right. Okay. Here's another one. Level sets. Again, there's a bunch of mumbo jumbo here. Let me lead into that with let's just kind of get some stuff on the page. Let's start with some examples. So looking here, I have a multivariable function. Okay, domain target formula. I guess I could draw the graph. I'm not really sure how to draw that graph. It's going to be a surface. Surfaces are hard to draw. Let's look for a different alternative. Right? The reasonable different alternative that I'm going to do goes as follows. I'm going to take the values of the function, always x squared plus y squared. I'm going to set them equal to various constants. So if I were to set, hypothetically, if I were to set x squared plus y squared, the value of the function equal to 1, okay, well, I know what that is. That's a circle, right? And so that gives me that picture. Likewise, if I set it equal to 2, now perfectly legal, right? It's a different thing. Just choose to set it equal to. Again, I get a circle. This time it has a slightly larger radius, so square root of 2. So something like that. So basically, for looking at different output values, what I'm doing here is just drawing what are the input points that correspond to these output points. Said differently, what I am doing here is I'm one at a time taking these input points and kind of moving backwards through the function. I think I said that backwards. I'm taking these output points and moving backwards through the function to find what are the all possible corresponding input points. And that explains this notation here. The fact that I am moving backwards through the function is why we write that with f inverse. Right? F inverse of 1, because I'm starting with 1 and going backwards. Now, this notation here, also an abuse. This function is not invertible. It's way not invertible, right? This output has not 1, not 2, but infinitely many corresponding pre-images, right? So it's definitely not invertible. There is no inverse function. So so that's a little uncomfortable using this f inverse. You just have to keep in mind this. In this case, this is not intended to represent a function. This is just a hacky kind of. It conjures the right image. Bad choice of words. It conjures the right idea that we are going backwards through the function f. So don't overinterpret from that notation. Okay. Okay, so that is what all of this stuff up here means. So all this stuff up here, for any given output value, for that output value, we're going to look for all of the corresponding input values that land on it. And recall, that's a pre-image. All righty. Everybody happy? Let me show you an example where I claim you've already seen level sets. Oops. Weather maps. Assuming you all have seen pictures like this. Let's see here. There we go. So pictures that look like this. You can tell it's really cold up here in Minnesota. It's really hot in Florida. And the temperature kind of varies in between, but as indicated. So you can see that, where we are in Durham, about right there. We're sort of halfway in between. We're halfway in the middle of the 50s range, and so you kind of get a sense that it's probably about 55, 54, 55, something like that. Okay. So, where are the level sets? How is this level sets? Let's think about this curve right there, that black line that I just drew here. What does that curve mean? Well, this curve is the barrier. It's the dividing line between values in their 40s and values in the 50s, otherwise known as this is where the temperature is exactly 50, right? And so again, the value of the temperature function on this curve is a constant, and thus this is a level set. That make sense? So every time you've looked at one of these pictures and kind of gotten a sense for temperature, you are already making interpretations from level sets. All right. Okay. Let's see here. Yeah. Here's another example. If you've ever done a significant amount of hiking, you may be aware of topographical maps, otherwise known sometimes as contour maps. And contour maps are called that because they draw a bunch of contour lines. A contour line is just a level set of altitude. It's what you get when you set altitude equal to one constant at a time. Right? So, for example, this, you know what I can do? I can just keep, okay. So this maybe represents where altitude is, let's say 300. And then this maybe is where altitude is equal to 400. And then on, et cetera, up that hill, down the other way, perhaps. So, so you end up with pictures that look kind of like this. And here's a real-world example of one of those. This is an actual contour map. I've zoomed in on a place that I think is interesting. This is called Mount Evans in Colorado. It's the highest paved road in the continental U.S. And it's a heck of an experience to drive that road because it's you're at a very high altitude. There's very steep drop-offs depending on where you are on the road, on one side or the other. You would tumble thousands of feet if you fell, and there's no guardrails. And you're at nearly 14,000 feet, and your brain isn't working right. So it's pretty scary, right? Anyway, if you're ever looking for a thrill, that's a good thing to do. Okay, so back to the original picture. Let me show you one little bit of good that you can get out of one of these contour maps, topographical maps. Let's suppose that I was here, and I want to climb up to the top of the hill there. Well, if there is a trail that goes like this, I'm not taking that trail. You know, and again, if you're a adrenaline junkie and you just looking for a challenge or something, but look how close these contour lines are. Each one of these lines, as I've drawn them here, let's suppose, represents 100 feet of elevation gain. That means that over this teeny tiny little bit of horizontal distance, you're gaining 100 feet of altitude. A little bit horizontal, a lot of vertical. That means it's very steep there, right? And I'm past the point where that's what I'm interested in for entertainment. So here's what I would do. I would follow a path that goes like that. Because, for example, it takes me quite a bit more horizontal distance to gain the same 100 feet as would have been a much more difficult hike between there and there. Right, so this can help you plan out your path, right? And roughly speaking, the big idea is when the lines are close together, that means it's really steep there, right? When the lines are far apart, it means it's not that steep. And so you get a very useful sense for the shape of the hill. Okay. All right. Okay, real quick observation I want to make here. See how we're doing on time. Okay, yeah. So neat fact, level sets are horizontal cross sections of graphs. We have these two pictures, right? Two different ways to understand a function. Level curves help me understand a function. Graphs help me understand a function. They're talking about the same function. Should be no surprise that they have a geometric connection between them, and this is it. The one is our cross sections of the other. So here's the way you see it. For example, let's see here. Here's the graph. Well, I'm sorry, I got ahead of myself. Here's a level curves, right? These are level curves, aka level sets, because I'm setting the value of the function equal to a constant. That gives me these curves right here. Then here's the graph. The graph is what you get when you set the function equal to a new variable. Same function. Just instead of setting equal to a constant, I'm setting equal to the new variable z. We don't yet quite have the tools to draw that picture, but I'm going to draw it anyway and promise that I'll fill in the blanks. You know, how do I know that this equation gives me this surface, kind of a bowl? We'll see that next time. Totally different pictures, and again, very, very important. Please don't think graph when you're looking at level sets, and don't think level set when you're looking at graphs. They're totally different. If you apply the calculus of graphs to the level set, you get garbage nonsense as your result. Makes no sense at all, means nothing. Yeah?
So is the purpose of the level sets just to help us visualize and
Yeah, it's another geometric tool. Yeah, it's when you can't do a graph, sometimes a level set is useful. We're also going to find that there's a bunch of calculus relevant to level sets that's going to be really useful. And so sometimes we'll want to rewrite a surface or what have you as a level set so that we can use the calculus of level sets. Yeah. So real quick observation, again, I claim that cross sections relates these because cross sections just means you're setting z equal to a constant, which gives you, you'll notice as you take these slices, the exact same circles, right, as the level sets. So hopefully no surprise. I think it's a nice observation to make. We'll call it a day there. Y'all have a great weekend. See you later.